Yeah, so we'll just wait for some more time. So usually how many students join these sessions? Any idea about the numbers?
Yeah, around 20, like average 20 joins, but today is holiday, right?
Holiday. Okay. Okay.
Yeah.
Okay. So yeah, I just want so till at least some 10 of them join. I'll just ask few questions, not technical, but just to get a feel because this is the first session I'm taking in this course. So I just want to know what you have all gone through.
Sure.
Right. So this is how you are all taking both MLP and MLT together, or
Yes, yes.
okay. So all of you here, Rajiv, yes. Others also, is it like that?
What was the last question, sir?
Yeah. So MLT and MLP, are you taking both of them this semester, this term?
Most people seem to have done that. I don't know, there may be a few who haven't, but most of the people who attend the sessions, I see them in both.
Okay. Okay. Right. All right. So that is one question I had. Right. The other is a rather important question. So have you all seen the lectures of week 5?
Yes.
Yes.
Oh, okay. So two of you have seen. So what about others? Can I ask? So that a lot depends on how the session goes. Depends on whether you have seen the lectures, right? So can others also comment whether you have seen? If you don't want to unmute, you can just raise your hand or wave your hand. There is some option, right, in Zoom or in the chat. Okay, Jaydev says no, but Jaydev, it's okay. I mean, you know stuff, so that shouldn't be a problem. What about others? Okay, we'll have to wait and see, right? So the reason I'm asking is this is quiz week. So typically what happens in a quiz week is week 5 goes for a toss, right? So that's why I'm not.
Absolutely.
All right. So, but I am assuming that.
Yeah, that is what is happening to me.
All right. Okay. So I'll assume that somewhere some of you have seen, some of you have not seen. So probably we'll go through some slides that I have with me, in addition to some slides that the prof has. So that will be a good mix, I believe. Okay, so that is another question. So another 3 more minutes, we'll just keep talking generally. So how have you been finding the course? Are there any particular difficulties? What did you like? So what did you not like?
Okay, the course is actually quite good. I like the approach of learning things from the scratch,
Right.
and but practically I have been learning more Python than this course. So I didn't realize that so much of Python would be needed for the assignments and part. So that is fun.
Right. Fair enough. Right. Yeah.
So today actually somebody is taking a session on NumPy because a lot of NumPy gets used in this.
Yeah, he's also here actually.
Yeah, that actually that was the Karthik's idea, because we just had this hypothesis that it's perhaps NumPy that is causing some issues, but turns out that is actually true. So that's why we are taking a sort of a broader look at NumPy.
Right. So see, Jaydev here is, I'm sure most of you will be knowing, he's actually been working in this area for quite some time, right? So there is no better person to take that particular session. So he'll be doing it at 5 p.m. So please do join that also. Right. So yeah. Okay. So I think we can get started, right? About around 10 participants are there. So
Yes.
all right. So you are all able to see the presentation, I believe.
Yes.
Okay. So the story so far has been this. So please don't mistake me if some of it seems repetitive or certain things. This is just tying together the last 4 weeks with week 5. So we have seen what regression is. So two broad classes of problems in ML. One is regression, where your output label is a real number and you want to regress or you want to predict that. And we saw two approaches, right? So linear regression, polynomial regression. Of course, polynomial regression is not really a new thing. We have just said that it is some polynomial transformation followed by linear regression, right? So that is not really two problems. It's just one particular aspect that we have focused on. And then we shifted from, so this was for first 3 weeks. So week 1 was an introduction, week 2 and 3 was on regression. And then we moved to classification. We have started doing classification since last week. And we have looked at 2 algorithms, right? Or 2 models rather. One is least square classification, which is largely based on the regression approach, and you just piggyback on that. And the other one is perceptron, right? So perceptron is not really a very strong algorithm, but for historical reasons, we have studied that because it will be very useful when we study neural networks in week 12, and later on in the degree level, we have some very interesting courses like deep learning. So this deep learning business will be all about neural networks, for which the foundation is going to be laid in week 12 of MLT and MLP, right? So that is some perspective. So that is where we stand. Okay. Now, there's a question to all of you, anyone can answer. So what do you think is one striking similarity among all the models that we have seen so far, be it regression or classification? What jumps out at you?
I think they all are linear. I mean, they separate the data with, I mean, by drawing a line.
Exactly, right? So that's a very good answer. So that is exactly it. So linearity is what is the unifying theme, or if you want to unify all of these things and put it under some basket, then as Harshad, I think, mentioned, it is linearity, right? So everything is, every single model that we have seen, whether regression or classification, it has started off with this linear combination. Okay, so you have a set of features, and then you, so before we move forward, so what is this linearity? One thing is sigma wixi or w transpose x, but intuitively, right? So they, this word we keep using often in ML and data science. So what is this intuition behind this w transpose x? Anyone has any idea?
It's a linear combination of the weights, right? The weights are linear.
Yeah, it's a linear combination of
the weights.
Weights, yeah. And so you essentially, but why is, what's so sacrosanct about this, w transpose x? So okay, what I want
is a convex function, obviously, because a linear combination, this is a convex function, so that helps in the optimization part.
Okay, that is one perspective. Coming from more application oriented perspective, what does say I have some xi, right? Some feature, some index in the feature vector xi. What does wi really mean?
How important that feature is.
Exactly, right? So that's what I was looking for. Of course, the convexity is also valid. So, but I had this same idea in mind that the importance of a feature, it's a very simple way to say how important a feature is. So if you have if x1 represents, let's say you are doing a regression problem, and x1 is the area of the house, and x2 is, let's say, the number of rooms in the house, and you are regressing for the selling price of a house. So how does the selling price of a house, say y, and depend on the square feet, area in square feet, and the number of rooms, right? So w1 in this case will tell you how important the area is, area feature is, and w2 will tell you how important this number of rooms feature is, right? So this linearity, one way of looking at it is it's a very smooth function, it's convex, and it helps us in optimization. That's the mathematical perspective. And the other perspective is that it gives you the sense of how important your weights are. Okay, so these are the two different ways of looking at it, right? Yeah, so linearity, and now we move on. So it is just expanding on the previous idea, right? So in regression, how did this linearity work out? Simple w transpose x. We said y equal to w transpose x. In polynomial regression, you just transform it and you still say w transpose phi of x. So in least square classification, okay. So in least square classification, okay, just treat this as some sort of revision also, since we are going over. Tomorrow, Friday, we have a proper session, but I just thought we'll just go over some of these things. So in least square classification, what does W transpose X stand for?
That is the projection.
Okay, all right. So what I meant to ask was, how is this W transpose X different from this W transpose X? So in the regression case and the least square case, how are these two different? Did I make myself clear? So what is the use of this W transpose X in regression and its corresponding use in classification? How do I use this finally?
So basically, yes,
Sorry.
please go ahead.
In regression, you are trying to actually the weights also contribute to the actual value of the label, right?
Right.
But here in least square, it is basically the sign that we are looking at.
Right, exactly. Right. So the way we use it matters. So as Srinivasan pointed out, here the exact value matters. So we are not just interested in the sign, but here it's the sign that matters, right? So the convention that we follow is if W transpose X is positive, it's we infer that to be class 1. If not, it's negative, right? So something similar, very similar in perceptron also, right? So this is linearity. So please keep this in mind. This linearity is you have 4 different. Yeah. Any
I
question?
have a question. Yeah. So does it mean that the value of weight will not matter in least square case?
No, it will matter. So it is just okay. That's a good question. So the exact value or the norm may not matter, right? So if you scale, that's a good point. So if you scale W, say if you have obtained some W's, you say replace it with 2W or 3W, it will still classify exactly like the earlier model, right? So I won't say that the weights don't matter, but the weights give you some direction, right? So perhaps you could say that the exact magnitude doesn't matter. Okay, so you have direction and magnitude. So in what is the orientation of my hyperplane does matter for classification. But if you ask me exactly what it should be, the norm of it maybe not.
Okay, thank you.
Yeah, but that's a good point, right? I think that's an important point. Okay, so linearity.
Multiple W's can give a good output for a perceptron, whereas for regression, only one W will give the best output.
Right, exactly. Yeah, that's the way to put it better. All right, so that is linearity, as we have seen. Okay, so now we come to logistic regression, which is the 5th model. Okay, third model for classification, but 5th model as far as ML models are concerned. Okay, so I am assuming now that some of you have not seen the lectures. So what I'll do is I'll quickly go over what logistic regression is all about.
I have that doubt again. So you said that the direction of hyperplane matters, but if its location is not right, it will still not work out, right? So
true. Yeah. So see, the location of the hyperplane is in some sense controlled by this bias term also, right? So if you decompose this as W naught plus W transpose X, right? So this dummy feature, you just pull it out. The exact positioning of your hyperplane is controlled by your W naught, right?
Right. Yes.
So I have a collab here, and I don't know if we'll have time to do the plotting business, but see, you are essentially scaling. You look at it this way. So you have y equal to mx plus c, right?
Right.
So the c is what controls the offset from the origin, right?
Yeah.
The orientation is going to be controlled by m. So m could be, say if m is 3, I could write down 3 as say 3k by k. Okay, just so your equation now becomes something like ky equal to 3kx plus kc, something like that, right? So you get the point. So the slope is what matters for the line, and the distance or where you place it is controlled by that bias term. Okay, so that's a good experiment. Maybe we'll take it up for solve with us next week. what happens if we remove this dummy feature? So we have been talking about this dummy feature all along, right? The dummy feature corresponds to the bias. So we shall actually see if we can train a model. Okay, maybe I'll ask that as one question. So if we train a model without the dummy feature, any of these, say least square classification model, I train it without the W naught term. So what do you think will happen?
Yeah, the plane will be always 0, 0.5.
The plane will be,
Like it will always pass through 0, 0.5. The time you change those that dummy parameter, then that 0 will get shifted to right or left.
No, it will pass through 0, 0, right? It will pass through the origin.
No, it doesn't pass through the origin. 0 and 0.5. 0.5 is the where the symmetry.
okay, I think you're talking about the
Sigmoid, yes.
yeah, no. So I'm talking about this thing, right? So let's say least
Okay,
square
only this part.
Yeah, so there it will pass through the origin, right?
Yes.
Yes.
Pass through the origin. The hyperplane goes through the origin.
Yeah. So that maybe we have to take it up and see how badly it fails when we try to train it without this
Dummy.
dummy, right? So the bias is important for that reason. That all right. So any other questions? Okay. So the logistic regression model you have. So even though the name regression comes there, it's a classification model. So here we are taking some steps towards nonlinearity, right? So far it's all been linear. This is also in some sense linear only, but we are pushing towards nonlinearity, right? And this is not achieved just through this polynomial transformation of features, but through something called the activation function. Okay, what is this activation function? It is something of this form, right? So it's called a sigmoid function, where you take a real number z, and then you squish it between 0 and 1, right? So you take any real number z, minus infinity to infinity, it could be any real number, and you push it between 0 and 1. Okay, so right. So why this particular choice of function? Does anyone have any idea why is this useful? Why not some other function, like sin z, say for example? That also pushes it between say -1 and 1, right?
0 to 1.
Yeah, in perceptron, like if we see that separation line, right, that is kind of a binary, right? If this threshold goes in the right side, then it will be 0 or 1. Say for example, -1 and 1. Say for example, like if it is greater than 0, and then it will consider it as a +1, and less than 0, -1. But here, at least since there is little bit of linearity, so that means, say for example, something is 0.1. Now whether to classify that as a +1 or -1, so it gives that kind of a flexibility. Like,
okay, right. Yeah, so I think
Another is it will be a PMF, right? Practically it's a PMF.
yeah. So that is probably closer to the answer. I think Jagdev was also posted in the chat that it's a probability, right? It's a probability mass function, if you want to be say precise. So anything that moves your z between 0 and 1, it takes on the interpretation of a probability, right? I can interpret it. So the interpretation is probability, right? So the model is still not saying I'm going to spit out a probability, but you interpret it as probability. Okay, so that is, we'll come to this. I mean, this will become clear in case it's not clear so far.
It's not clear for me.
Yeah, it will become clear. So I kind of jumped 2-3 slides, so that's why it's I'll come to that. Okay, so just for now, just remember that this is something called sigmoid function, which pushes your inputs from real space to real line to 0 to 1. Okay, so that is all. This mapping alone you need to remember. Okay, so what is this black box? Again, this is a theme that will keep recurring throughout this course and also other ML courses. So we need to look at a model in two ways, right? One is looking at it as a black box, meaning what is the input, what is the output. Okay. So if you look at regression, for example, input was some number x, some feature vector x, output was some real number. Okay. And if you look at classification algorithms, typically output has been some class label 0, 1, 2, right? So this kind of an understanding is also important. So what is the input and what is the output, right? So the output is a label, but what is the label actually represent? What does it represent in the case of logistic regression? For those of you who have seen the lectures, can you tell me what it represents?
Can you reframe the question once again, please?
Yeah, so the output is a label, that is clear, but if you look at the actual output of a regression, logistic regression model, it outputs something, right? What is that? What quantity is that?
That
Even
is
if,
a
yeah,
discrete number actually. Like
right.
yeah, that is a probability.
Okay, yeah. So that's what I want to know. It's outputting a probability, as you say, right? What probability is that? Probability of what? So if you want to be more precise, is
Yeah,
it probability?
probability of the class level given that x. It is a conditional probability.
Okay, yeah. So that's a good point, and that's a very important thing to keep in mind, that the logistic regression model outputs a probability. More precisely, it outputs a conditional probability where you are conditioning it on the input data point, right? So this is extremely important to note, right? This is the whole idea of the model. So if you understand this, it's like you have understood most of what logistic regression is, right? It takes in an input and it outputs the conditional probability, right? So are there any questions here? Okay, I hope not. So yeah, so the point is, what's the probability?
Here,
Yeah.
if there are different classes, different labels, so for every label, we'll get a different probability value, right?
Okay.
Right.
This is for a binary setting, whatever I have shown here.
All right.
But yeah, what you are saying is right. So for a multi-class setting, we haven't treated the multi-class setting in this. So probably we'll restrict it to binary for now, right? So this is the logistic regression model for binary classification.
But sir, here then it will give two probabilities for two labels, is it?
Yeah, it will always give you. So the model, I design it in such a way that it always outputs this particular probability. So probability of seeing 1 given x.
Okay.
Okay, so that is, yeah.
And the other probability of y equal to 0 given x is 1 minus this.
The complement thing.
Right.
Complement,
right.
yes.
Yeah.
Okay, yeah, good. Thanks.
Okay, so this is a Bernoulli. If you want to treat it as a proper distribution, it's a Bernoulli PMF. So Bernoulli random variable. Okay, so where we are outputting the probability of a success, where success is seeing a 1. Okay, so that is another way of looking at it. Okay, now we move on. So that the other way of approaching a model is just the complement of the black box approach, where you look under the hood and see what's happening. So here what's happening is you accept x, you do a linear combination, and this basic linearity that we have been seeing so far, W transpose x. And then you apply what is called this activation function, this nonlinear activation function, sigma of W transpose x, right? So going back, what is sigma? Sigma is this. Okay, so note that this is a real number. This is a real number, not a vector, not a matrix. This is a real number, and W transpose x is a real number finally. Okay, so this takes in an x and then it outputs some real number between 0 and 1. And this we interpret as the probability of seeing the class label 1 given x. So is there any question at this stage?
No.
Okay. All right. So once we have the model in place, we know what the model is. Now we have to look at the learning problem. So what are we going to learn? We are going to learn the weights. Right. So we are going to learn the weights, and there are two approaches, right? So there are two approaches to learn the weights. One is parameter estimation, which you have all studied in stats 2, I believe. So you have studied maximum likelihood estimate and some other estimation schemes also, but we will focus on parameter estimation using maximum likelihood estimate. Okay, the other approach is to minimize what is called as the cross entropy. Okay, so what is this cross entropy? We'll come to it. I'll give a very brief, to whatever level I understand, I'll give a very brief idea of what this cross entropy is. But for the purpose of this course, you need to understand that this parameter estimation using MLE leads to this cross entropy,
Yeah.
right? So that is, and they are equivalent is what you need to understand. Okay, so how do we estimate the parameters? All right, so the first thing is, we assume that the data, samples from the data are drawn in an IID manner, right? So I think this is something you're all familiar with. You are just drawing samples from this data and they are all IID. Okay. So this is again something that is subtle, but we need to know there is some joint distribution that is producing these data points. Okay, so there is, see, when you look at the class of data points that you have, right? Think about all possible data points. You don't usually see them as X and Y separately, right? So these X and Y kind of they reside together. All right. So the positive and negative samples, this demarcation that you're doing, even before that, there is a stage where they're all mixed together, right? So the entire positive and negative samples are all put into one bucket. And when you draw samples from your bucket, you're actually drawing from or sampling from this joint distribution. Okay. And then what you do is you just rewrite this as P of X into P of Y given X, right? So this P of X here is actually the PDF of X, which is not very important to us because it doesn't determine the W, right? So the parameters of your model are not dependent on this PDF. So you can actually get away with that. So is this point clear or is there any confusion here? Because this maximum likelihood will keep coming.
That?
Okay, so which part did you understand this? Why we are doing it?
I got it till the part where you said that we're trying to assume that the given distribution is a joint distribution, and what we have picked up, we have to sort of guess which class it is from. Did I get this right?
Okay, see, this part is correct. That is, they all come from a joint distribution. And then what we do is, I won't say that. So see, this is purely a mathematical transformation we are doing. P of X comma Y is P of X into P of Y given X, right?
Yes.
I am just expanding this as this.
Right,
okay.
Yes.
And since my parameters, since I'm modeling what? I'm modeling the conditional distribution, which depends on W. I'm actually not interested in PDF corresponding to X.
Okay, you just are interested in probability of Y given X has already occurred.
Yeah, okay. So I can get rid of this P of X.
So sir, isn't this P of Xi equal to 1? Because like the time you are giving the subscript I, that means this data has already been observed. So that means probability of happening that is only 1, right?
No, I don't know, right? So in that case, P of Xi comma Ya itself I can treat as 1, right? I mean, I have drawn Xi, Ya. So I don't think you can interpret it that way. So it is more like I am ignoring P of X. I'm not saying that P of X is equal to 1. What I'm saying is, for the purpose of this parameter estimation, this P of X is something I don't need because W doesn't depend on P of Xi, right? So I see the data, the actual data points without the label, let's say. And that is not in any way tied to my parameters of my model.
The words training data is going to be constant for us because somebody else is giving that to us. We are not generating training data ourselves, so the model doesn't control how the training data is coming. It is coming from the world, or it is coming from your client, or it is coming from some process, which anyway we cannot control. So only thing we can control is W.
Yeah, I think that's a better way to put it, right? So this is already something that the world, or Jaydev said, the client is giving you, the environment is providing you with all this. So this is not tied up with your W, right? So the W here determines only the conditional distribution.
So let's say if you are building some sort of a spam classifier and we started tuning on X itself, then we'll have to tell our users that, you have to send emails which correspond to that particular X, and only then I'll work.
Right.
Only then I'll be able to identify something as spam or not spam.
Right.
That's not what we want to do. What we're trying to say is that whatever data you send, as long as it is representative of whatever data you have been sending so far, I can still do my job.
Right. So I think that should have convinced you. Right. So we'll move on. If not, we'll maybe get back to this. Okay. So I kind of get rid of the PDF of X, and I'm left with just this as my likelihood. So the lectures, this is what likelihood means, right? So let's just stick to that. In case all of what I said was confusing, you can ignore that, right? So if you look at the lecture slides, the likelihood begins from this, right? So just treat that this is the likelihood you are trying to maximize this particular likelihood. All right. So before I go to this cross entropy and other things, I'll probably just shift to the slides. Just give me a second. Okay. So did everyone understand why this particular thing came about? So you have your likelihood here, and it's the product of the probabilities that you observe for n data points. How does this step morph into this? So is there any confusion there for anyone?
No, because this is writing the same thing, because once y equal to 1, the right hand side will be like 1 minus hw, that part will be only 1. And if y equal to 0, the first part will will be 1. So that way it is just expanding that so that we can do the final differentiation, because we are taking care of both the samples, both the types.
Okay.
If it's not a lot of trouble, can you just go over this once? I've not seen the lecture.
Okay. So see this there may be too many functions here, so that might lead to some confusion. So HW of X is nothing but this what I call the sigma of X, right? So it's W transpose X, and then you apply the non-linearity on top of it. Okay. So
basically it's a Bernoulli, right? So that way one is the other is
right. So
correct.
Yeah. So if you want to, let's see, if you want a proper way of doing this, so Y is Bernoulli of, let's say, P, right? Say some parameter P, then what you are saying is, where is this? So you're saying, what is the probability of observing Yi of Ya? See, Ya could be 1 or 0, right?
Yes.
So Ya could be 1 or 0. So what you do is you rewrite this as P power Y into 1 minus P power 1 minus Y. Right? So, sorry, this Y should go to the top. Okay, so what this effectively means is that when Y is 1, it's just the probability of seeing the class 1, which is P itself. And if Y is 0, it's 1 minus P, which is nothing but the probability of seeing class 0. So this particular formulation, it gives you the probability of seeing class Y. So if you expand it, in case this is still not clear, PR of 1 will be P, and PR of 0 will be 1 minus p. So you have made use of this fact and written it this way.
Yes, got it. So this is the Bernoulli likelihood when we are looking at only one instance.
Exactly.
Okay.
Yeah. So
Yeah.
this is just one instance, and then you multiply it across n samples, and
Okay. Yeah.
and then you take the log, because it's much more easier to work with logs, log likelihoods than likelihoods. And this rest of it is standard math. So your loss function is now, so maximizing the log likelihood is what we are trying to do. But since in all problems that we have done so far, in all models we have minimized some loss function, we can treat minus LW as the loss, and then we'll try to minimize the negative log likelihood, right? So that's what sir means by this transformation here.
Okay. Okay. Got it. So we want maximum value so that, yeah, got it.
Right. So this is okay. That's all the slides are kind of going to get over. So yeah, so the real question is, suddenly we are calling this binary cross entropy loss, right? So far we have been calling it negative log likelihood, and now we also call it binary cross entropy, right? So this could be confusing. So what I'll quickly try to do is tell you what this entropy business is all about. Okay, so entropy is a term that comes from information theory, right? So it simply means this how much uncertainty is there in a random variable. Okay, how uncertain is it? You are quantifying that. That is what entropy is. So to take an example, so this is the formula. Okay, so this is you will see where this comes from, or how this ties to our negative log likelihood formulation. So for now, just look at it this way. Entropy is given by minus p of x sigma minus p of x log p of x. So this is nothing but the expectation of this value log p of x, right? For this particular over this random variable, you are taking the expectation of log p of x. All right, this will still be confusing. So let's take one example of the Bernoulli random variable, say p, okay, with parameter p. So if you apply this formula, you'll get this minus p log p minus 1 minus p log 1 minus p. Okay, so this is the entropy. And if you plot the entropy with respect to this parameter p, you notice this nice concave curve coming up. So can someone interpret this? What is happening? What is the meaning of this curve?
The expected value would be the maximum value of the function, right?
Okay, so
no, it's not the expected value, but yeah, you're kind of on the right track. But let's go on.
Okay, so maybe I didn't clarify that. So see here, each value of p corresponds to one expectation, right? You're computing the expectation over that particular random variable. So each point, this whole thing is not,
a function. Okay, I get it. Okay,
yeah.
I think I got confused, but I can sense
Right.
it. Yeah, see, basically in any time, right? Even when we study in stats, so you could have any function of a variable, random variable, right? The expected value is the same formula still.
Right. Okay, so what's happening is very crudely. So what we said before is that the entropy is the measure of uncertainty, right? So what does it mean? Let's take some value of p which is very low, like say 0.01 or something like that. Then you see that the entropy is low, right? What does it mean? It means that when your value of p is very low or very high, then you are much more close to certainty, right? So think about a biased coin, which will land tails 90% of the time or 99% of the time. how much uncertainty does that particular random variable have?
Yeah, much lower. You can
very low, right? So that is what this entropy is computing essentially. So when your P is 0.5, when you have a fair coin, then you have maximum entropy, and that is what entropy signifies. So what we have is not, yeah.
But say, for example, like you are saying that entropy is the measure of uncertainty, right?
Right.
So that means like lower the probability, it is more uncertain, right?
No. It is it's a Bernoulli, Rajiv. It goes to the other way, right? So if suppose here P is the probability of a head, right? Very heavily tail biased coin. I know that the probability of head, I can just say it is 0 always, right? And I'll be more right? So that way it is far more certain that it's going to be tail rather than a head. So either the
you can think of this as betting on, for example, like let's say you're betting on whether tails will win or heads will win. At what value of P would you be least comfortable making a bet? And assuming that you're making a bet based on how confident you are a certain thing, a certain sequence of events will come.
Okay.
I know I will be I'll be completely not comfortable placing bets on P equal to 0.5 because absolutely anything can happen and there is no way that there is very low predictability to a sequence of events. Whereas if it goes to either side of 1 or to either side of 0.5, my confidence in one value or another value increases.
Yeah,
which means less uncertainty.
Like in a cricket, suppose you give a cricket analogy, right? I mean, India, South Africa, India, Australia, it's difficult to put a bet, right? I mean, somebody outside. But India, West Indies, I can clearly say that West Indies is very likely to lose, right? So that way, both a West Indies fan as well as an India fan will be comfortable betting that way.
Because now let me ask a clarifying question. Okay, say for example, you have a document, okay, and you have like a lot of words. Now the word that has less frequencies. Okay, what will be the entropy? Like high or low? I know they will appear low.
See, the entropy you must tie it up to the random variable, right? So
yeah, so there also the random variable is occurrence of that particular word.
So it's basically this, like that same words in a document analogy can be modeled with let's say throw of a die. You have only 6 words, all of them are equally likely in case of a die. But when all of them are equally likely, then the entropy of that die throw is maximum. Because you can't prefer one particular face of the die over the other. Whereas, if you're talking about actual natural language, for example, then entropy is much lower because most words are, a lot more common than other words. Or less common, whatever.
Okay, so what you are telling is like if there is a uncommon word, right? So that entropy is low, right?
As well as very uncommon word as well as common word. So entropy of the and entropy of Zeitgeist would be very similar. See, the is very likely to occur a lot, and Zeitgeist is, I probably did not even pronouncing it right. It's going to appear very low, right? So both the entropies are low.
No, actually, there's a problem here. We do not talk about the entropy of a single event.
Yeah, okay, I get your point. Okay, sorry. Okay.
Of course, if you say that the event is a word occurring or not occurring, then that's a binary Bernoulli variable for each word, right?
Yeah.
Which again means that it's a different problem completely.
Same thing. Like say for example, you have a Word document, and there some particular word which occurs. Say for example, in 1,000 words, it occurs only once or twice. Okay. Now the occurrence of that particular word is kind of a random variable.
It is an event, right?
Yeah, occurrence of that particular. So that is an event. So I can I can come up with a random variable like the occurrence of that particular event, occurrence of that particular word, and which is extremely low because 1,000 words and that word came only once. So it is 1 by 1,000.
So that has very low entropy, right? If you
that's the question, like whether it has a low entropy or high entropy.
Yeah, so if you have either very rare events or uh, or events that occur very frequently, and you want to model, you have a random variable associated with that, then that will have a low entropy, right?
Yeah, but actually, like if you see the information theory literature, like what entropy says, entropy is the amount of information present in that, present with that random variable.
Okay, so I think so. See, that interpretation comes when you say that how much information does the outcome give me, right? See, for example, if the outcome of tossing a coin, very biased coin, right? No, I don't have much information to gain from that. So in that context, what you say is correct. So you can interpret it that way also, right? So the amount of uncertainty is low. When the amount of uncertainty is low, there is not much information I can gain out of it.
No, say for example, now it is a winter season, okay, and say for example the temperature is kind of 7 degree, okay, and if I say that tomorrow there will be a tomorrow the temperature will be 40 degree, okay, the information content in this for this like is very high. If I say tomorrow is 7 degree, then like information content is very low because that is quite normal,
Okay.
isn't
Yeah.
it?
Maybe. So this discussion, unfortunately, I can't clarify beyond this because I haven't read the information theory literature. So maybe you can maybe post it in Discourse, and in case one of us can answer it from that perspective, we will. But otherwise, this has to unfortunately remain limited to the ML context, right? But if you post the question in Discourse, I will also do some thinking, digging up, and see if we can have a discussion. Okay.
Yes.
All right. So for the purposes of this discussion, I hope this understanding is clear of what this entropy actually is about, right? So again, this is not from the point of view of the exams, right? This is just to tie these things together. So cross entropy again is in a very crude sense, right? Please don't take this literally. It's measuring the distance between two distributions. Okay, so you have one distribution which is the true distribution P of x, and Q of x, let's say, is the model distribution. So you're trying to model the true distribution. So how do you interpret it? So P will be the true labels in some sense that will give the probability of seeing a true label, and Q will correspond to the predicted label. Okay, so that is how we tie back to this equation here. So if you go back, notice the formulation of the laws. It is minus yi log h of xi plus 1 minus yi log 1 minus h of xi. So this is the reason why we call it cross entropy, right? So I know that this is not very convincing, but for the purpose of this particular discussion, I think this is all we can do.
Yeah, now like if I ask another question, like if you go back to the previous slide, okay, now here px is coming from the true level, okay,
Yeah,
and qx is coming from the predicted level,
right.
okay. Now what is the like physical intuition of this cross entropy? Is it the kind of you have two different probability distribution and you are trying to find out some kind of a distance between them?
Yeah, that's what it is. It is, see, there is something called the KL divergence. So the right
Yeah,
term should be the KL divergence. So the KL divergence, that's also not a very proper distance metric, but that gives you some kind of distance between two distributions,
two probability vectors.
two probability distributions. Yeah.
Okay, okay.
Okay, but yeah. So so why is it binary? Because we are talking about Bernoulli random variables here. So we just stick to binary cross entropy. Okay, that's okay. I think that's enough of entropy that we have discussed. So now, what is the geometry of the decision boundary for a logistic regression model? That's the next thing we need to ask. Okay, any answers? Anyone?
Straight line, right?
It is again a straight line actually, yes.
Straight plane.
Okay. right? So, but we have non-linearity, right? So will that non-linearity not affect our decision boundary?
So actually, like even after non-linearity, we are using a thresholding. We are using some thresholding, right?
Okay. All right.
So then, like, yeah, that was one of my question actually. Like, kind of, we have a non-linearity induced here, but still we are using some kind of a thresholding. So how different it is from perceptron?
Okay, I think these are all very interesting things. Okay, so okay, just before we go there, so others, are there any questions? So a lot of others have been quiet. So am I missing out on some of you? Are there any questions so far? This entropy part you can forget because that is not a part of the course per se. But apart from that, are there any problems so far? Okay. I don't seem to get any other response. So I'm moving on.
I wanted to clarify if you'll be able to take out some time to discuss week 1 to 4 at the end, maybe.
Sure. Okay. Yeah, that we can do. That will happen tomorrow also. But if we may have more time on our hands, so we can do that also.
Okay. Thank you.
Okay. So this decision boundary, right? So what is the geometry? So yeah. So this part, I hope it's clear. It is one if the probability is greater than 0.5, as Rajiv mentioned, the threshold is 0.5, 0 otherwise. Okay. So how do we go from here next? What is the next step? What is this for a logistic regression model?
This is a logistic regression model, right?
Right. Yeah. So what does this translate to in our model? Can I replace
half
this?
space.
Right. So this entire thing is the half space.
Half
But
space,
even
yes.
say even before that, just the probability, the conditional probability, what can I replace that with?
H of x.
Right. Right. So I have just used a different notation. I have just called it sigma of W transpose X, same as H of X, right?
Yes.
Okay. So all right. Okay. So this being greater than 0.5 is nothing but. So what will be the next step? So sigma of W transpose X. See, W transpose X is Z. So that being greater than 0.5 will lead to what? What is the next step?
You'll say that Y is label 1, right? So you'll say that the probability of Y is 1, or we predict the value to be true. 1.
Yeah, so here the label. Yeah, so here we are talking about inference, right? So Y is 1 if this happens and 0 otherwise. So the probability was here, and this is the label actually.
Yeah.
Right. So did I get your question correctly, or?
No. Like my question was different. Say, for example, if you go back to the previous slide,
This is the starting.
the diagram.
Yeah.
Yes. Now here, probability is greater than 0.5. What does that mean essentially? Is basically your this line, right? 0.5 line, and that is your x-axis, correct?
That is your the z-axis. Let's say z-axis.
Okay, perfect. Now here also you have used the thresholding.
Right.
Okay, how different it is from your perceptron, because there also you are using thresholding.
Correct. Yeah, we are coming to that. So if you can complete this step, so what will be the next step in terms of
calculating the loss and like then finding out the gradient stuff.
Right, but no. So maybe the question.
I have a question.
Yeah, right.
So I have a question. So is the sigmoid function like kind of scaling? Are we scaling all the data points to fit into 0 to 1?
Yeah, so we are downscaling, or maybe sometimes some kind of, I won't say scaling, but we are trying to push all of them between 0 and 1. So we are trying to push all data points. We are not so we are transforming them into this probability space. If you think about it. So every data point X, we are trying to associate a conditional probability with it, which lies between 0 and 1, and the sigmoid function helps us do that.
Okay, and so if I assume that it was scaling down, we could have used a straight line as well. Why the non-linearity?
So if you use a straight line, right, say W transpose X itself, you're saying that will not lie between 0 and 1, right? It can extend beyond 0 and beyond this interval of 0, we want to see, if we go back.
No, so if we did a conventional scaling sort of something and then used a straight line, would that still work?
it won't look like a PMF, no? So it won't have the area will not come as 1.
No, like to your question, like you are not scaling the X, you are scaling entire W transpose X. You are not scaling X. X you have something, okay, and once you multiply with W transpose, you are getting a linear combination. That linear combination can be greater than 1, right? And to make it a probability, you are scaling it down between 0 to 1.
And what do we mean when we are saying that it is getting converted into a PMF?
Because
is this
you are
becoming a
using that
normal
sigmoid,
distribution?
right? Since you are using that sigmoid, so your values are kind of between 0 to 1, right? And that is kind you can think that as a probability measure.
See, what's happening is so if you look at this black box approach, what we want to do in the case of logistic regression is we want to take an X as input and we want to output a conditional probability, right? So this, if you think about this as your objective is to take some input and spit out one probability.
Right.
Okay, and not just any probability, but the probability of seeing a class 1 given this X. So you want to output this particular very specific conditional probability you want to output. Therefore, you necessarily need to have the output of the model to lie between 0 and 1, right?
Okay, yes.
And that is why you take the help of sigmoid function. Now, your question is, why can't it be some linear function which just pushes the values down to 0 and 1, right? Why can't I just divide by some, say, maximum of W transpose X?
Yeah, or like Rajiv said, maybe we could have just normalized or something the values of X such that those only lie between or something, some kind of scaling down. Yeah.
See that, let me take a simple scaling, right? So the usual one normalization that we can do is divide by the maximum of.
Yes.
Right, but
maximum of X.
Yeah, but that really won't work, right? So see, you are you sure that it will always lie between 0 and 1 for test data points as well? Of course, we are using this whole IID to understand that they'll all come from the same distribution. That's why our models even work. But still, that is whatever training data you see, and if you normalize based on that and expect it to hold for during the test time, that's a bit dangerous. This is much more principled way of doing it, right? Pushing it between 0 and 1 using sigmoid.
And in fact, like probably sigmoid is not the only function. You can even say, for example, 1 by e to the power x plus e to the power minus x. That will also thrash it down between 0 to 1, and you can use that also as a probability measure.
Right. So you could use different kinds of
different functions.
Yeah.
Okay. Thank you.
Yeah. So moving on, we were at this stage. So okay, now sigma of W transpose X should be greater than 0.5. Okay, so that is our condition. That if that is the threshold, then we say it's class 1. So we need to complete this. So what will be the next step? What does the sigma of W transpose X greater than 0.5 mean? With respect to the sigmoid function,
if the probability is greater than 50% of being 1, then we are like probability of W transpose X Greater than 0 is greater than 0.5, then only 1. No, same thing I am repeating actually, nothing. No.
Yeah, but so the question is with respect to the decision boundary, what does this mean? So you want to see our goal was to see how the decision boundary looks, right?
Right.
So with respect to that, what if I want to find out what the decision boundary looks like, where do I go next with this information that I have? Okay, so I just go back. See, we started off with this question: what is the geometry of the decision boundary? And for that we asked. So for that we need to look at the labels that this model predicts. So it is 1 if the probability is greater than 0.5 and 0 otherwise. So this will hopefully give me some idea of the decision boundary. That took me to this, because the probability of y equal to 1 given x is sigma of w transpose x. Now from here, if I want to know using this information what the decision boundary is, how do I go about it? There is one small step that we need to do.
Not sure.
Yes,
For
so
now, it
we
seems
do
like
a
there are
parameter
two
grid.
functions.
Sorry?
If we do a parameter grid, say for example, this W.
Okay. So right. So I'll just maybe I'm not putting it correctly, or there's so
No, but like we got the question, but not able to
right.
answer actually.
Right. So
Yeah,
this,
because there are two functions, so it's confusing.
okay. So this is what it translates to, right? So it translates to, see, when is sigma of something, sigma of z, when is it greater than 0.5? Whenever z is greater than 0, right?
Yes.
So what does that correspond to? That corresponds to w transpose x being greater than 0.
Greater than 0, right?
Okay. So and therefore our decision boundary is a hyperplane in m-dimensional space. Or if you are talking about 3D space, it's a plane. Or if you're talking about 2D space, it's a line, right? But it's linear. Finally, we come to that conclusion that our decision boundary is linear. Okay, so is this jump clear from here to here?
Yes.
Okay, so that is the decision boundary. So after all this, we finally come to this point. I think Rajiv also made this point. How is, I mean, what is it really different? How is it different from perceptron, right? If you look at it from just the point of view of decision boundary, or even least square classification, right? In least square classification, what did we say? We said W transpose X greater than 0, it is 1. Otherwise, you call it 0. Right? In perceptron, what did we say? Same thing. Only we change the label to -1. That's all. So in logistic regression, after doing all these things, we have still come to the same conclusion that if W transpose X is greater than 0, it is 1. Otherwise, it is 0. So how are the three different then? Is there any difference, or?
I'm not able to see how they are different.
Okay, so we'll come to that. So just give me, let's take some 3 minutes break. Okay, at 3:05 we'll meet again. I'll be on the call, but I'll just get back to you in 3 minutes. Please stay on.
Okay.
Okay, so yeah, so far are there any confusions? So till this part, because the rest of the discussion needs this part to be clear on why the decision boundary is like this, and right. So but for a few participants, rest of you have been silent. So any reasons why? Any reasons for this silence, or is it usually like this? Okay. It is also met with the silence. All right. So shall we proceed?
Yeah.
Okay. So we have the same decision boundary, the same formulation. So seems for all three classifiers that we have seen so far. So it is a hyperplane linearity all over again, right? Even after using so-called nonlinear activation function. Okay, so this I think will be quite general, useful for all 4 weeks and for the weeks to come hereafter, right? So what really happens to this weight vector when the gradient is subtracted from it? Okay, see, gradient descent is it's probably the, as Sir mentioned in the videos, workhorse of optimization. So lot of ML is based on this gradient, computing the gradient and using gradient descent. So what exactly is happening to the weight vector? So that is what we look at, right? So this notation, I think by now it should be clear to all of you that this is m cross 1 weight vector, gradients. N cross m is x, but since you're doing transpose, it's n cross n, and the gradient in the case of logistic regression turns out to be this. So there's a whole derivation for it. Do you want me to go over the derivation, anyone? Or can we skip it?
Yeah, we can skip it.
Okay, so there is a whole lot of stuff, but this is quite straightforward. If you sit down and work through it, you will see that you finally end up with this value. Okay, X transpose the output of the logistic regression model minus Y. Okay, so that is the way you have to look at it. So this is nothing but the predicted output, right?
Correct.
Or the probability minus Y and X transpose. Okay, so that's all it is. Okay, so this is something that we have not seen so far, and I felt that this is a useful way of looking at the gradient. So is this transformation clear?
Yes, yes.
Okay, others, what about others? Is it clear to you also?
Yes.
Okay, so what we are essentially doing is, this is one way of multiplying a matrix and a vector. You are just, so if you look at it, you are just scaling, each training example by the error in prediction. Okay, so this is the prediction error. Sigma of xw is the output of the model, y is the actual label, e is the error, and you are essentially scaling each training example by its error. That's what the gradient actually looks like, at least in this case, but it's also true for least square classification and other things, as we'll see. So this is a very important step. Is this clear? Can I move on now?
Yes.
Okay. Okay, so what happens to the weight when the gradient corresponding to a single data point is subtracted? Okay, so let's take the simplest case of SGD, stochastic gradient descent, where you don't compute the gradient or the entire training data, but you just do it for one training example. So for one example, what will this become? This will just become x into error, right? The data point into the error.
Right.
Okay, so that's the gradient. No, the gradient is data point into the error corresponding to it. And now we come to this gradient vector, right? So this should not be gradient vector. This should be the weight vector. So I'll correct it later. The magnitude Okay, no, this is the gradient vector, right? So the magnitude and the direction of the vector are determined by these two things, the data point and the error. Okay, so I'll just use this terminology. E is equal to y pred minus y. Okay, now we are moving on. Okay, so this is I mean, not a visualization, great visualization, but just to give you the idea of what is happening, both in the case of perceptron and in the case of logistic regression. Let's take this weight vector W. So -3 is the bias term. So this actually corresponds to the equation 2x1 plus 3x2 minus 3 equal to 0. That is this hyperplane, or that is the weight vector currently. Okay, now x is this point, 1 comma minus 3. Sorry, minus 3 comma 2. So notice this is minus 3 comma 2. Okay, 1 is the dummy feature. So this is minus 3 comma 2. Weight vector is pointing in this direction. It is normal to the decision boundary and it is of this form. Okay, now if I take a point, so at this stage, what is actually the label, predicted label of this blue point, blue data point?
Negative.
Right, so is that clear to everyone? Rajiv has answered, but I would like others also to.
No, I didn't get the drawing only. Can you go over the graph once again?
Okay, so see, this is so 2x1 plus, see, the weight vector is what you know that the weight vector is normal to the decision boundary, right? Or the hyperplane.
Yes.
In the case of, yeah, so that is this red vector is this minus 3 comma 2. Okay, not minus 3, 2 comma 3. Okay, so this W0, W1, W2. So this line is represented by 2x1 plus 3x2 minus 3 equal to 0. Is that clear?
Yes, yes.
Okay, so any point above this line is going to be classified as positive because W transpose X greater than 0 means 1, right? So for all points in this half space or half plane, you are going to say it's positive, and anything below this or in the opposite direction of W but below this hyperplane, you are going to call it negative.
So blue line is basically W transpose X equal to 0.
Blue line, yeah, this blue line is W transpose X is 0. This is greater than 0, and anything here less than 0.
Correct. And that is the reason X and W are perpendicular.
Okay, so that, yeah, sorry, that is my mistake. It looks, so it need not be perpendicular. So it could be any point here, right?
No, what I'm telling is like any vector on that W transpose X equal to 0 on that line.
Okay.
Your W is perpendicular to that.
Right, yeah. So I thought you were talking about this.
No, not this one. On that line.
Right, yeah. Okay, so it so happens that Y predicted is 0.04. If you substitute the formula of sigma of W transpose X, you will get Y predicted to be 0.04, meaning its class predicted label is 0. Now you do this update. Okay, what is the update? W is equal to W minus data point into error, right? So that is, so error is what? Minus 0.96. So this becomes W plus 0.96x. So is it clear so far?
Yes.
Okay. So if you do this update, let's see what happens to the hyperplane. Okay, the hyperplane gets rotated or it gets shifted in such a way that this blue color data point X is no longer classified as 0, it is now classified as 1. Okay, does that make sense?
Yes, because your W got changed with the W plus 0.96x, and based on that, like now your decision boundary is again perpendicular to that W. So that is the reason it has taken care of that particular point. Now that point will be classified as 1.
Right. So in this particular example, it so happened that it moved properly, or it moved enough so that it classified this point as 1. Right.
Correct.
So this is what is happening in one update of your gradient descent, of stochastic gradient descent. So it is essentially moving your decision boundary around. Each update moves your decision boundary in a favorable way so that what was misclassified becomes properly classified. Okay, so again, this is a very crude picture, but yeah. So is this any questions? If you have, please stop me, otherwise I'll move on.
Correct. So through that iteration, like it is picking up one points and adjusting that W transpose X plane.
Right.
Yes.
Okay, so now what is this similar to? Isn't this very similar to perceptron?
Absolutely.
Right. So actually, I mean, I won't be wrong in saying that SGD with logistic regression is very close to perceptron.
Yes.
Right. SGD with logistic regression is very close to perceptron.
Yes, yes.
All right. So
so basically, in essentially, like we didn't get much benefit from inducing that non-linearity.
yeah, but right. So we'll come to that. So there's just one small difference, right? So in the case of perceptron, you add X and you subtract X on different occasions, right? So,
Correct.
But in this case, if you notice, Y predicted is always going to be less than, okay, no, here also you do the same thing. So if Y is 0 and in one case you add X, in one case you subtract X, with this error term alone being different. Okay, so
yeah, exactly same thing. Like in perceptron also, you are moving that W transpose X like that only.
Right. Okay, so now I will just pause and ask. See, only 2 or 3 are responding. So Shruti and Srinivasan, is this clear to both of you? Only 3 of you are responding. So I need some kind of
Yes.
confirmation to know if this is all right. Of course, Rajiv is responding, but only 3 of you are responding. Anyway, so so here is where we look at what happens to a point which is already correctly classified. So see, blue is here. This is your decision boundary. And Y predicted is 0.99, actual label is 1. So this is already correctly classified. So what do you think is going to happen to the update? So I do this update. So W equal to W minus X into this. That becomes W plus 0.01 times this X. So how do you think the decision boundary will look like now?
Yeah, the
Will
decision
it
boundary.
move closer to the data point? I'm just guessing here.
Okay, closer to the data point. All right, then what else? What other answers?
So it will rotate, but that point will be still classified as +1.
Okay, so let's see what happens. It's very close to the previous one, right? So there's no perceptible difference between the previous one and this one, right? This was because
correct,
the error term is also pretty low, right?
Yes.
Okay, so if you compare this with least square classification, now do you remember there was a slide where Professor Ashish talked about least square classifiers being prone to not robust to outliers. Do you all remember that there was a mention of that? Okay, now logistic regression on the other hand is going to be very robust to outliers, because if I have already predicted something correctly, this error is going to be very small. Okay, I'm using very so often, but yeah, this is going to be pretty small. So this is not going to disturb the current value of the weights at all. Okay, notice that this is again similar to perceptron, where perceptron doesn't care about examples which have been classified correctly. Its worry is only about misclassified examples.
Yes.
Okay, so these are some of the similarities and differences. So if you actually run an SGD on this data set, this is what is going to happen. So can somebody see what's happening here? Something interesting that you find with this particular progression of SGD?
Yes, like after it has classified all these things, like very slow movement actually, then it is just aligning. That's all.
Right. So I have one question, for which I also don't have the answer now. I haven't thought about it a lot. So maybe we can start a discussion on discourse. Why even after classifying, right? See, it classifies perfectly after 10 epochs. Why is it still rotating? Why is it still? What is the reason for this alignment?
Yeah, the reason is like in my mind, say for example, you have that sigmoid function, right? Unless and until like it goes in saturation, gradient is still flowing, because your W transpose X, say for example, if you open up that sigmoid curve, okay, there if you go beyond 4, right?
Right.
Yeah, see, beyond 4 if you reach, right, that time almost it will stop, because your learning is now saturated. Now it is not learning anything. But if you are in the region, say for example, between -2 to +2, so still like lot of gradient is flowing.
Right.
And that was one of the reason, like, yeah, that was one of the reason. Say for example, if we use a min-max scalar, okay, if we use a min-max scalar for this logistic regression, there could be essentially a problem.
Okay, what is a min-max scalar?
See, min-max scalar will scale down your data between 0 to 1. Okay. Now, say for example, your all your x's are between 0 to 1, and assume that you have all w's initialized to positive value. Okay. Now your W transpose X itself is going beyond probably 4, right? You have a very slow learning, and if it is more than 5, it will not learn also.
Yeah, so this has actually been normalized to 0 and 1. So this has been,
and that is the reason it has to be normalized to standard scalar, not max min scalar.
Okay. I didn't understand this point. Can you repeat?
Yeah, so if you go to that sigmoid curve, that figure, I can explain better.
Okay, so what he's talking about is something called this vanishing gradient problem, right? So for that, I have a slide for that. We will just make. Okay, not the slide. We take up this particular. So what he's essentially saying is that, see, this is the derivative of the sigmoid function. Okay. And whenever you hit very low values or very high values, your gradient saturates or it becomes 0.
Okay, so the gradient is the derivative, right?
Yeah. So that is going to slow down your learning, right? So your gradients are going to be pretty small. So this is a classic problem known as the vanishing gradient problem, right? So we'll come to this in week 12, so or maybe in the next course, right?
Okay, and here we don't have the concept of step size, right? Why is that?
Step size as in learning rate, you're saying?
Yes, there, learning rate.
Yeah, that is there.
Yeah, we do have. So for SGD, right? SGD or any gradient-based method, we are going to have some kind of a learning rate.
Okay, that's still here.
Yeah, that's still there. So for this particular animation, I've used learning rate to be 1. So it doesn't seem to affect all that much. Okay, so but this is still a question that I would like to fully understand. Maybe we can have a separate discussion on this. Okay, so comparisons, we have, if you look at the gradient, so finally the gradient is what matters. For logistic regression, we just saw that it is sigma xi ei, where ei is the error. Same is the case for least square classification, sigma xi ei. Okay, for perceptron, it's minus xi yi, right? So here there is no error. The error term is either 1 or -1. So we have this. So does this slide make sense?
Yes, yes.
Okay, so now notice 1 and 3, they look so similar. So what is the only difference?
In the
1
first case,
and 3 are the, yeah.
yeah, so I think in the first
please
case,
go on.
we were not even considering the ones that were classified correctly, I guess.
Okay. See, in the first case, what is y-pred, and in the second case, what is y-pred?
First case is without the sigmoid.
Exactly. Right. So that makes a lot of difference, right? So first case is without the sigmoid. It's just some real number. So it could be anywhere. So it could be all over the place between minus infinity to infinity. Whereas here it's between 0 and 1. Okay. So this is what makes logistic regression more robust to, say, outliers as compared to least square classification. Right? When you have least square classification, it's going to penalize you for correctly classified examples also.
Yes, yes.
Right? So it's going to be bothered about those which are classified correctly, and see what is W. See, this is what in the case of least square classification. What is this? It's just X transpose W minus Y, which is what, in some sense, very roughly speaking, X transpose W is the distance from the hyperplane, right?
Correct, correct.
So if you have an outlier which is way out, so way out of your hyperplane's current location, that is going to contribute hugely to your error term.
Yes, yes.
Right. So that's why your decision boundary will keep swaying when you introduce new points which are far away from your current existing blocks. And that problem is not there with logistic regression.
Correct.
Okay, so I think that is roughly what I had for week 5, and we have some questions in the portal, which are, if you have any questions about specific activity or practice questions, let me know. We'll discuss that.
So, is there any issues since the sigmoid function is not centered around 0?
Sigmoid is
the centered as 0.5, right? So, is there any potential issues there? So, for example, your all W's are positive, okay? If all your W's are positive, then you will be always in the right side of the sigmoid curve, right? Is it possible you can still go back to the negative other side, or it can only go to some W's can be positive and some W's can be negative? It can happen in that kind of situation.
So if all W's are positive, still that X might bring in some. So it's W transpose X, right, which finally decides where you end up.
Yes, yes, yes. My question is, say for example, if I see the W transpose X, right? If all W's are positive, then W transpose X is positive, right? Okay. But not necessarily.
Provided X, yeah.
Yeah, because X is between -1 to
depends
+1.
on
right?
X also.
Correct. Okay, no.
Yeah.
Not valid question. Yeah.
Okay, so what I will do is I will quickly do two things. I will go through this activity question and see if there are any issues that you have with them. So logistic regression is a discriminative classifier, right? So
True.
this is false. can it be used for binary, multi-class? Can be used for both, right?
But isn't logistic regression
One
is
and two.
your discriminative?
Yeah, it is discriminative, right?
Yeah, so true, right?
I mean, it's asking
Oh,
non-discriminative.
sorry.
Yeah. Okay, so there are m features, then you have m plus 1 parameters.
M plus 1, yes.
Right, so that is, I hope this is clear to all of you. So we'll just move on. Okay, so what are the answers for this? Loss function used?
Binary cross entropy and negative log likelihood.
Okay, this is convex. Okay, so this is just going through the motions. So let's just quickly close it. Again, you can use any of this, right? So you can use any of this. So, right?
Yeah,
So
precision
precision, recall, F1 score, root mean score alone you don't use. Okay, so that is that. Activity 5.4. Okay, this is a repeat binary, multi-class, multi-label. You can essentially use it for all of them.
Yes.
This is just the form of the logistic function.
Yeah.
And this we have been seeing so far, right? What is the gradient? X transpose sigma of xw minus y plus lambda w.
Yes.
Right? 5.5 is... Okay, so if it's linearly separable, then you don't need polynomial transformation. Right?
Correct.
Learning curve is between
number of iteration and errors. Yeah, correct. Loss value.
Okay.
Yes.
Yeah. So 5.6. So you probably need some transformation for non-linearly separable classes. And for real-world problems, can we determine the degree easily? No, right? So we can't determine the degree of polynomial so easily. So we'll have to do probably some kind of
grid
tuning
search
to find out.
Yeah, cross validation.
Yeah. This has only one question. The correct expression for loss. Again, I think you can refer this from the notes from the slides.
Yeah, third option probably. No, there is an there will be two negative signs.
Yeah. So this negative is outside of the whole thing. So,
yeah, and outside, right?
Right. So for those of you who are, this is all basic stuff. So in case you are not very sure about this, don't worry. Practice questions. This is practice. And we have the theory practice. Yeah. Okay. Again, so this is along the same lines, right? So is there something that anyone wants me to discuss? So we will.
I think these are pretty much like straightforward from the lecture actually.
Yeah. So I will skip it. And yeah, so that is roughly it. Okay, so are there any questions that anyone has? So really, how do other sessions go about? Like, do they get completed so fast or?
No, actually, like earlier session were like they were going through these these activity questions pretty slowly. But
Okay.
Since today you have taken the first one on concept building, right? So it was fruitful because we can easily converge into this quick convergence on these activity questions. But
okay.
Yeah, to me, like this kind of session helps actually. Like instead of going through like all these activity questions, like but it is completely like my perception.
All right. Okay. Yeah. So see, got over so fast. So I'm just wondering. I just go through the collabs. That is something I haven't done.
I think Shruti told like if we can discuss at least some part from the like week 1 to 4. Yes,
Shruti. What exactly
So I didn't get the multi-output regression case, and I also did not understand how you could use logistic regression for multi-class thing.
Okay. See, the logistic regression for multi-class thing, you have to come up with multiple weight vectors. Okay, so each one corresponding to one class. So, for example, you have so you have this p of y equal to 1 given x. You are modeling it as sigma of w transpose x, right? So this is for single binary classification case. So what would happen if you took up, say, some class C? Then you would have something like not sigmoid. You have to use something called a softmax. Okay. So we haven't actually introduced softmax, and I'm also not. I'm a bit rusty on softmax, but I will get back to you. Right. So what you do is you create a discourse topic, okay, and tag me. We will discuss on how to use the softmax function for multi-class classification with this framework. Okay, so it's basically this, say, WC transpose X, and you have many such WC transpose X. What you do is, roughly I'm telling you this, I may not be totally correct, so okay, so for not the probability, I won't call this probability, no. You, for each one you have, if there are k classes, then you can come up with, so very similar to this multi-class setup for least square classification, right? You had one k class discriminant function, right? So you have something similar to that, and to convert all of them into probability, what you can do is you can raise them to the power of e. Okay, and sum it over e power w r. Sorry, I'm missing it.
Yeah, W transpose X.
Right, so some WR transpose X where the summation runs over all possible classes. Okay, so I will just point you to this for now.
Why not just max of probabilities?
So max of, so what is your notion of probability here? So you're saying sigmoid of W transpose X for each one and then say max of that.
Yeah.
See, we are no longer in the domain of, so you're talking about it in the form of one versus all, right?
Yeah.
So see, one versus, yeah, so that's a good point. But what we are trying to do here is, it's more of a categorical distribution, right? It's not a Bernoulli distribution. We are looking at this as this probability, right? What is the probability that y equal to class C given X as a, so what we need in that case is, if you sum these probabilities over all possible classes, okay, that should be one. So that is a categorical distribution, right?
Right, yes.
Okay, so if you want to come up with that, then you have to take this particular formulation, which is where is this Wikipedia entry? Okay, so see, you use this for multinomial logistic regression, and you raise it to the power of z, and then you sum it over the whole thing. So this acts as this squishes your k-dimensional vector into this 0-1 space.
Yeah, but if you see the softmax, right, and argmax, Okay, in case of this multi-class classification,
Hmm.
like they are no different, because like argmax also, say for example, you think about MNIST data set. Okay,
Okay.
so at the output you have 10 classes, 0 to 9.
Correct.
Okay, now you get something, say for example, given X, you get like your 3 has a probability, say for example 0.39, and rest all are less than 0.39. Okay,
Okay.
even if you do that argmax, okay,
Hmm.
you will get it correctly classified to 3. Okay, and
Right.
even if you do that softmax, you will get it 3. The reason being, your softmax is a monotonically increasing function,
And also it's differentiable. So that's also there,
yes,
right? So
correct.
yeah, valid point. So if you have max, something like a max, you can't differentiate it. So in most of the, if you use it in your loss function, when you take the derivative of the max, it's like not going to help you, right? So you go for a soft max because of that. Yeah, valid point. Okay, is that clear?
Yeah, somewhat. And about the other case, the multi-output regression thing, how do you learn different weights from the exact same data set?
Okay, multi-output regression. So I am probably not the right person because I
So see,
was
like in that case as well, right? Like basically what you are doing, your all inputs, think like your all inputs are connected to only like each and every position of the label. Say for example, your Y is 100 or 010, this kind of thing, right? Like
No,
for multi,
multi-output regression, when you are giving out real values as outputs.
yeah, like okay, you are saying correct. So even in that case, say for example, whatever you are learning for column 0, right? So that time only thing, like your weight vector is changing. Like earlier your weight vector was say for example, you have 10 input features, so 10 cross 1, right? In multi output, you the number of weight vectors are, say for example, if you have 3 output levels, then
You'll have 3
10,
weight vectors.
correct, 10 cross 3, not 3, 10 cross 3.
Yeah, and 3 row and 3 columns is what I
Yeah,
meant.
and now think about like each of them as kind of one regression problem. So you are solving essentially 3 different regression problem there.
That's what I'm confused. Is it not the same regression problem, because the data set is same and ideally they should all converge to the same value of weight, no? So all the output should be the same, but how are we expecting
No. Say for
difference?
example, like you have 2 features, okay? 2 features, the way it impacts the first level is not same as the way it impacts the second level.
There is no label, no?
No, label in the sense I am saying you, say for example, your output is 3, say for example, your output vector is 2.35, 3.75 and 4.5, right?
Okay,
Your
yes.
target.
Right.
Correct. Now, the way your input features are impacting the first column, that means where it is 2.35, is not same as how they are impacting the second column.
Okay, got it. Okay, so,
Got
yeah,
it?
I got it. Yes.
So now
So the
basically you are
training
solving
data.
3 different regression problem, one-dimensional regression problem.
Yes, got it. Thank you.
Yes.
okay. So just to conclude, I will just go through this collab, right? Because that is, even though maybe this is not the right time, but still, for the sake of completion, I am supposed to go through this. So this is the logistic regression collab, okay? Yeah, so model is all the theory that we have seen so far. Why the conditional probability, sigmoid, all this we have seen. And you can just vectorize it as xw. Okay, so the first function that SAR uses is linear combination. I know this should be extremely familiar to you. It's just x at w.
Yes.
Okay, so the sigmoid again is very simple. You just, all this is
1
just
by e
the,
to the power minus
yeah,
x.
it is also clear. And when you are predicting, when you leave out all this part, you're looking at threshold, and when your linear combination, sigmoid of the linear combination is greater than threshold, for all those indices, you say that the output is predicted label is 1. For the others, you say that the predicted label is 0. Okay, so that is the prediction for logistic regression. Now let's move on. This is just some examples, right? So for some feature matrix, if you have some weight vector, what is the class label, right? So that is that. Loss functions are as explained with regularization, and all this is gain. So what is the loss? Loss is nothing but the binary cross entropy loss we have been seeing so far. You multiply the actual labels with the log of the prediction, and 1 minus y with log of 1 minus y. Okay, and then you just sum it across all the entire list, and then you get the loss. Okay, so and then you add regularization with some lambda here. Okay, this is L2 regularization, by the way. Okay, we have L2 and L1. So this is a bit of both. Okay, so optimization, calculating the gradient, we have seen this X transpose sigma of xw minus y. Okay, so it's the same thing. What about, finally we come to the class logistic regression. This is just putting things together. So your class, you have a variable, instance variable self dot w. This is linear combination sigmoid, then applying the sigmoid on top of the linear combination. Here predictions are as done slightly differently from the previous one. Wherever the activation is greater than threshold, you have some booleans, so he is converting them to integers. Okay.
Yes, yes.
Loss again the same thing, nothing different. Gradient also we have seen. Now gradient descent. So by now I think you are all familiar with how gradient descent works. So you have some gradients computed, then you just update the weights.
Yeah. Now we can write a gradient descent at least in the midnight as well.
Yeah. Right. So this toy data set, I think last solve with us you were asked to do this. So this is polynomial transformation, the same thing again. If you remember, all this you know.
Yes.
So now you are training, splitting the data into train and test, and this is the visualization. Okay, and you have gradient descent on top of this, right? So a learning curve is again pretty much the same thing. Okay, this is the contours for visualizing the decision boundary. Okay, and the classification report that you get for each class. Now polynomial least square we haven't discussed much, but I think it's just the polynomial transformation and then logistic regression on top of that. Okay, so we just do the polynomial transformation on the feature matrix with degree 2, and then you do logistic regression. Okay, so here you have a circular decision boundary, which is what you want to arrive at. Okay, and so that is it with respect to the collab. Okay, so any other questions?
Is there one thing like is there any use cases where we can chain these two guys, like say for example classification followed by a regression?
Classification followed by a regression. That's a good, yeah, there are I don't immediately recall anything. I can't immediately recall, but that's a see. There are cases where you would want to differentiate broadly between two classes. So, for example, in the past, I used to work on one defect classification problem, right? So, where you have some, say, manufacturing parts, some of which are defective, some of which are not defective. So your task is to basically classify or weed out the defective ones. Binary classification problem, right? So you need to identify given an image of a machine part, is it defective or not? So here, what I might also want to do is I might want to ask the question, how defective is it? So
The
let's
degree
say,
of defectness.
yeah, the degree of defect. Right.
Correct.
So I could model it as you said, where I first train a classifier to divide this into two buckets, and then for the defective bucket, I train a regressor.
Right, right.
Right. So that's a good modeling approach, maybe in some of these situations.
Correct. In fact, like that is a nice example. Another thing I thought, like, okay, intermediate plane, like if you can learn some important features out of the like input features. So for example, you have like 100 features at the input, right?
Right.
In between, if you can learn some important features and then pass that to a regressor or something, like it is a classification followed by a regression problem.
Right. So yeah, so now that you bring this up, so we could also in fact look at classification as a regression problem itself, right? In the sense that
absolutely, because it is a regression, we are just using a threshold.
Right. Yeah, I mean, in the sense of say the degree, again, I go back to the degree. So you can, instead of classifying and then regressing, if you directly want to output, say, how defective the product is, I could directly train a regressor on it, like say 0 to 1 or say 1 to 3 different scales for how defective a product is. We could just directly train a regressor and yeah,
but actually, like if you see like that kind of a problem, the approach that you told, right, first you run a classifier and then go to the regressor, that way it will be like that model will be more robust because you are first filtering out all the like bad examples.
Right, yeah,
correct. So like can you put up some kind of a video on that, like in Collab, like how to do that? So probably at least like we can try that out.
Okay.
Like how to mixing these two guys together, like but if you ask Ashish sir, like if he can like put something in the Collab.
Okay, sure, we will think about it. Yeah, that is a possibility. Okay, any other questions?
Would you recommend some resources, because I was finding it slightly tough to come across good ones?
See, Bishop is the standard reference we follow. Christopher Bishop, Pattern Recognition, Machine Learning. Have you taken a look at that book?
I have downloaded, but books are obviously difficult to learn from because you have to.
See, you have to look at the correct sections of the book. But I get your point, because they will start off somewhere where you may not have the necessary background to. I mean, you may know all these things, but they would have used certain notations. Resources.
And also maybe if you could arrange for some support to getting initiated to Kaggle or starting some work around that domain, maybe. Is that possible?
Yeah, so right. So Kaggle, you can start by exploring. So you have this Titanic data set and you have few other data sets. They have this never-ending competition, right? Which you can, anytime enroll and just keep practicing. So there are things like that. But again, what you make is a valid point. We need to identify the right sort of competitions or activities in Kaggle also. right?
Right.
So something that is accessible to someone doing ML for the first time. We'll think
Right.
about it, right? So we'll have to go through the list of active competitions and also the list of this ever active or ever always running competitions. I don't know what they're called. So
Yeah, at
called
least
There
like
is a called practice competitions itself.
okay. They're called practice competitions, is it?
Yeah, so if you just go to kaggle.com, you'll see a list of currently active competitions and they are classified by the reward.
Okay.
One will be like the live ones where just click on the competitions tab to the top left. Yeah, so here you can filter them out. Playground, community, those are the kind of things that, so for example, there it is, just new to Kaggle, just there you see the 3 ones that you have.
Which
Just
one?
go
Which
back.
one? I'm sorry, I missed it.
Go back to competitions, yes. So you see that new to Kaggle question right under your, yeah, just scroll down. Yeah, these are the ongoing ones forever. You can keep doing these.
Oh, nice. Okay. Probably, yeah. So maybe Jaydev, this also we should, if you can,
Yeah.
suggest
In fact,
something.
Karthik, they do have something called Kaggle for the classroom.
Okay.
So what we can do is, I'm not sure about finances and all, but we can run a Kaggle competition exclusive for us.
Right.
absolutely, yeah.
So we won't be like, for example, the Titanic one has 13,000 teams, but 14,000 teams almost.
Right.
So we won't be competing with all of them, but with say whatever, a few hundred students that we have, we can have a competition for ourselves, which will be hosted by Kaggle.
Because I think in stats too, like Andrew sir has done one of that, and like on that T20 prediction, right?
The IPL prediction.
Yeah, IPL, yes.
Okay, so we'll explore this possibility. So I recall participating in one such in Kaggle competition for a particular course. As you said, finances. I'm also not sure. I'll have to.
I think it should be possible to like find some. I think find somebody who's connected with Google somehow and
Right. Okay.
maybe get a discount or whatever. Let's see.
Right. Okay, so I think that is all we had today, and so the next session by Jaydev is coming up at 5 p.m. So please be ready for that. That is on linear algebra with NumPy.
Yes.
Okay, so
I'm sorry in advance. We sort of ruined everybody's Republic Day. I think we total have 5 hours of lectures today, but we try to make sure that doesn't happen again.
No, I think as long as it will certainly be interesting, right? So yeah, from next time onwards, we can schedule it appropriately. So
if possible, like either schedule it in the morning, like today is holiday, so there is no problem. In the morning, I think you have a schedule like Thursday you host at 7 to 8 or something, and Sunday 11 to 1 or something.
Right. The Sunday one is for TDS, and that one is, I think, Anand's schedule. So Thursday morning 7 to 8 is also a bit too early for me too.
That Anand, like like one question I was thinking yesterday, that Anand is like that he's a student or like he's from the POD?
So he is a student.
Okay.
There may well be another Anand who is in the POD.
There are a lot of
6 Anands that I can remember at least.
Yes.
I'm talking about Anand Iyer. So
Anand Iyer. Okay.
Yeah.
Okay. All right then. So thanks for joining.
And sir, you please think about that problem, like classification followed by a regression. Like if you can put some code, okay?
Okay. Yeah. Sure. Yeah.
Okay.
Thank you.
Thank you.
Thank you, sir.
Yeah.
Thanks.
Yeah. Thanks for joining on.